looking at the topic of absolute entropy in Atkins. This is a very short section, but conceptually, I think it's pretty profound. So his leading question here is, how is entropy measured? So we've seen images like this where heat's added, it can increase the temperature of our substance. The temperature could stay constant during a phase change, but as long as heat's being added, we see that the entropy continues to go up, up, up. If we're seeking to do a calculation within this, well, we have a starting point. It starts at zero entropy. As we begin to heat the solid, temperature changes, and we would be looking at the heat capacity of the solid in order to calculate the entropy change. When we reach a phase change, well, we could use, for example, the enthalpy of fusion. What we're tracking through here is we're looking at, as we add heat, how is the matter responding to it? For the different contributions for the heat capacity, what I'm thinking about is how it's translating in the XYZ direction. I'm thinking about how it's rotating based on the freedom of motion that would be present there. During the phase change, I'm thinking about how the particles are changing their position. The important thing here when we're looking at the absolute entropy is we have a 0 point. We've defined 0 as 0 degrees Kelvin for a perfect crystal. We don't have a 0 point like that when we're looking at other thermodynamic quantities like enthalpy or the Gibbs free energy. For those, we're always looking at a change. But in this case, we've defined something that is uniformly 0. But the closest that we have for those others is we defined something like the standard enthalpy of formation, where we're defining it for the substance in its standard state, and we could then do comparisons for, I don't know, gold and copper and other things. But the point here is we've got the same 0 for everything, and we're then now just tracking through how does the entropy change as we add heat. That's the concept here for absolute entropy. So if I'm thinking about what takes place here at the particle level, I'm thinking more particle motion, more accessible microstates, greater dispersal of energy. All of these are going to be things that lead to greater entropy values. I'm thinking about that when I see these reported values here for the standard molar entropies. So think about what this means. If we're doing a comparison, for example, where diamond has a lower value than graphite, which has a lower value than lead. In each case, we started with 0 entropy. We started with the diamond, the graphite, the lead. We're conceiving that as what did it look like in its crystalline form with absolutely no particle motion at 0 degrees Kelvin. That's what we're imagining there. And we're considering then how the particles of matter were affected as we added heat and we increased the temperature all the way from absolute 0 to this room temperature right now. That's what this entropy value is telling us. So as I'm thinking about this, all of these are going to be solid. So I've added heat, and in each case I was along this path here where I was interested in the heat capacity. Now with diamond versus graphite, in order to reach 25 degrees C, they responded differently. I ended up having more particle motion in the graphite. That comes back to the structure of how the structure of diamond and the structure of graphite are different. That's how I would be explaining the difference there. How about with lead? Well, with lead, I think I've got one feature. They're heavier atoms for lead than it would be for carbon. And we've seen that in a quantum mechanical description, that makes more microstates accessible, and so that would lead to a greater dispersal of energy. Back to sort of our particle in a box description. Now, if I'm looking at that, I'm also thinking, well, lead is a metal. Is that somehow important compared to like a network solid here? So in order to do that comparison, I looked and I thought, well, let me choose a metal that has a smaller molar mass, like lithium, smaller than carbon. And sure enough, within here, notice how its entropy value, it's not as large as lead, but it's larger than either diamond or graphite. That suggests to me that it has greater particle motion. When I'm thinking about graphite, I'm thinking how it has restricted motion in a particular plane, and then it has some motion up and down outside of that plane because graphite are these sheets of carbon atoms. When I'm thinking of a metal, I'm not thinking of a restriction like that. I'm thinking how it has motion in the X, Y, or Z direction that can be more robust than if it was restricted in this other, something like graphite, or even more restricted within diamond. So once again, I'm thinking I started as a perfect crystal, I'm adding heat, and I'm reflecting now. I'm thinking about the resulting particle motion that has taken place. How about for H2, N2, and O2? Well, all of these have much higher values than if I was looking at carbon or lead or lithium. Well, because these are all gases. So first thought is I can rationalize why those are higher is because think of all the particle motion that has taken place as it went from crystalline O2 all the way to molecules of O2 gas. Now, if I'm looking more closely then at these and I want to compare each of these all being gases, what would explain the higher entropy value or the ranking that I see where H2 is the smallest and O2 is the largest? Well, I've got two potential factors that I want to consider. How about the strength of the bond that would be there and also the molar mass? Well, if I look at the ordering in terms of the bond order, I would have put N2 as the largest. If I'm looking at it in terms of molar mass, I'd put O2 as the largest. Sure looks like it's best explained in terms of O2 mass. Now, if I think about this a little bit more deeply, the difference in bond order, I think that would be affecting the vibrations that can take place. I don't think the bond order would be affecting aspects of the translations, the rotations, but it would be affecting aspects of the vibrations. And in a higher order way of thinking about this, I don't think the vibrations are really active in either case. I don't think that those are accessible. So that's why it makes sense to me that the best aspect of the description comes back to features of the molar mass. So if I'm thinking about things that would lead to a higher entropy, there's things that are leading to greater particle motion, a greater response of matter when energy is being added to it. Weaker bonds, heavier atoms, greater complexity, the phase. Is it at a higher temperature? How about the volume it occupies? Or more particles? In particular, ones that are quite pronounced. Is it a gas? Is it a higher temperature in a larger space? And recalling that it's an extensive property, so if you have more particles, higher entropy because you can disperse the energy across more possible microstates. So if we're looking at this feature, which I use in my 1220 course as well, of putting together a ranking with these, this ends up being the ranking from the greatest entropy to the smallest. And what I like to now do is to say, well, how do we explain this? It's set up so that we have this unique ranking. How would we begin to explain it? What takes place at the particle level? So in one case, I would have an explanation involving differences in the mass of the particles and the complexity. Different ways that you can see the mass, different aspects for rotations for a diatomic versus just a single atom, the complexity, the volume it's occupying, and you see the different features there. Now, in the Atkins text, it goes beyond this. Instead of just naming these, it also has representations like this to show that, if you recall, that the shading region is saying how much energy do you have to populate different energy levels? How accessible are the different energy levels? How many particles do you have that you're using to populate them? This is all within that kind of representation. So as I think about these, within this class, within Atkins, I think, okay, now how would I begin to say, this was one scenario, what would the other one look like when I'm doing comparisons here? So for example, if I'm comparing these two molecules here and thinking about how there's differences in mass, differences in complexity, I'm not adding any more energy to those. For the same amount of energy, for the same temperature right here, what's taking place is the spacing of the microstates is changing. That's true if I'm looking at any of these features. In any of these features, without the temperature changing at all, I can have the microstates move closer together so I have more of them that can be populated. When I'm thinking about something at a higher temperature, I don't need to change the microstates, but I can now populate more of them because I have it at a higher temperature. Extensive property, the energy doesn't need to change, the microstates don't need to change, but I've got more particles now that I would add that can now disperse the energy. So within each of these, within the Atkins one, this is sort of how I take it up a level. I consider not just what's taking place at the particle level in terms of explaining it with these terms, we add it to this kind of representation as well. Now, since we have these absolute values, we can calculate the entropy change involved with a reaction. I oftentimes would lead this by, first of all, make a prediction. Given what we have right here, instead of just looking things up, can we make a prediction? These are the values. You see you have a really large difference when we're comparing a liquid with a gas. And I think within the other features, we can come back to the same other aspects as well of trying to explain what's going on. When we do the math, we're going to set it up as products minus reactants within our set, and we'd find in this case, the entropy of the reaction went down. And if we're looking at this, if I wanted to explain it, first thought, a very great indicator for us, a very powerful one, would be did the number of moles of gas change? Because those have such a dominant term when we're trying to do comparisons. So within this section right here, on absolute entropies, there's some calculations that we can do, but I've added to it, Atkins doesn't quite name it. I think we can make predictions and offer explanations for these entropy values as well. So I like these types of questions that he has, where we're listing in order these and we would be explaining our reasoning. We're making a prediction. Another example here where now it's a chemical reaction without performing any calculations. Explain your reasoning for the entropy change. Here's another example as well. For all of these, then, if I'm summarizing this particular feature, we have a sense to be able to explain why we have absolute entropy values and why that is so beneficial. We can consider what does it mean to now have standard molar entropy values. For each of these having this progression of beginning at a value of 0 entropy and asking, what did it take in order to reach room temperature? What kind of particle motion has taken place? We could explain that using these microstate representations. And finally, we can make predictions along with calculations when we have the entropy change for a reaction.